At 7:04 for UTC this morning, May 30th, 2026, Sunspot region R4455, a region that did not exist on the solar disk 6 days ago, fired an M1, 2 class solar flare directly from the Earth-facing hemisphere of the Sun and triggered a confirmed R1 level radio blackout that swept across the sunlit face of the planet, disrupting high-frequency radio communications above the Indian subcontinent, a landmass home to more than 1.4 billion people who went about their morning without knowing that the star that gives them life had just reached out and briefly silenced the sky above their heads. If you rely on this channel for science that is grounded in verified data and explained with honesty, subscribing ensures that none of this reaches you late. This work depends on the audience that values it. Every figure in this script was drawn from official scientific and governmental sources: NOAA's Space Weather Prediction Center, NASA's Solar Dynamics Observatory, the European Space Agency, EarthSky's verified solar monitoring reports, and peer-reviewed research published in institutional journals. But official sources are not infallible. And neither is the human process of reading them before any decision is made, whether personal, professional, or otherwise, verify independently through the official channels. The sources are listed. The data is public. The responsibility to check belongs to all of us. But that is not even the complete picture, because R4455 is not the only region the Sun has placed on this side of its disk in the last 7 days. It is not the second, and it is not the third. What the official data actually shows is that Earth's facing solar hemisphere is currently displaying 11 active sunspot regions simultaneously, with 3 of those R4455, R4454, and R4453 having emerged within a single 28-hour window ending on May 27th, and among those 11 regions. The one that concerns solar physicists most deeply is not the one that already fired. It is R4446. R4446 carries a beta-gamma magnetic field configuration, the most complex and energetically loaded classification currently visible on the Earth-facing solar disk, and it has been observed evolving rapidly, gaining a gamma component over the past 48 hours in a development that multiple monitoring stations flagged in real time. The question is not whether R4446 is capable of generating moderate to strong M-class flares or potentially stepping further up the classification scale. The question is when, and the instruments are watching it right now at this precise hour, with exactly that uncertainty written into every reading they produce. Here is where this account becomes genuinely significant: 11 active sunspot regions on the Earth-facing solar disk, 3 of them emerging within a single day, 1 already confirmed, 2 have produced an M-class flare and an R1 radio blackout, another carrying the most complex magnetic architecture currently visible on the Sun. And all of this occurring inside the extended solar maximum phase of solar cycle 25, a cycle that the international panel of scientists assembled by NASA and NOAA originally predicted would be a relatively moderate event, anticipating a peak smoothed sunspot number in the range of 95 to 130. The Sun did not cooperate with that prediction. Solar cycle 25 peaked in October 2024 with a smoothed sunspot number of 161, dramatically exceeding the panel's upper estimate, and as of this morning, May 30th, 2026, the Sun has not retreated into quiet. It is still accumulating, it is still energizing, it is still placing new magnetic structures on the hemisphere that faces your home. To understand what our 4446E's beta-gamma configuration actually means, you have to picture something. Imagine 2 bar magnets pressed together with their poles aligned in opposition, north facing north, south facing south, and then imagine that arrangement embedded inside a structure the size of a small continent, threaded through with magnetic field lines under tension so extreme that when they finally break and reconnect, they release energy in seconds equivalent to millions of nuclear detonations. That is what a beta-gamma sunspot region is. It is not a dark blemish on the surface of a distant star. It is a compressed magnetic weapon pointed at this moment at this planet. Victor Rogas, an independent observer in Sedona, Arizona, captured R4446 in filtered broadband white light on May 28th and described it simply: the Sun is peppered with sunspots at the moment, and R4446 is the largest and most active. That is not dramatic language from a scientist reaching for effect. That is a careful observer choosing the most accurate words available to him. Peppered. 11 regions at once. That is not normal quiet Sun behavior. That is a star in the full expression of its maximum activity phase, showing you everything it is capable of. The R4455 flare that fired at 7:04 for UTC this morning delivered what NOAA classifies as an R1, a minor radio blackout on a scale of 1 to 5. Minor, on NOAA's scale, means weak or minor degradation of high-frequency radio communication on the sunlit side of the Earth, occasional loss of radio contact, and degraded low-frequency navigation signals for brief intervals. The word minor is doing a great deal of work in that sentence, because the people for whom HF radio is not a background convenience but an operational lifeline: maritime vessels in the Indian Ocean, aviation crews crossing equatorial corridors, emergency coordination networks in regions where infrastructure does not permit any other form of long-distance communication, experienced on this morning something that the instruments labeled minor and that they experienced as silence. Silence in a communication system is not a neutral event. It is the system telling you it cannot tell you anything. And this morning that silence arrived without warning, covering a sunlit arc of the planet that included some of the most densely populated territory on Earth. Now consider what is approaching: a partial halo coronal. Mass ejection was registered by the Lascaux C2 coronagraph at 22:30 UTC on May 26, 4 days ago. That ejection, originating from the far side of the Sun, is currently in transit through interplanetary space and is projected to deliver a glancing blow to Earth's magnetosphere on or around May 31st. A glancing blow from a CME is not a direct hit, but it is also not nothing. A glancing interaction with Earth's magnetic field can still drive the KP index upward, can still produce geomagnetic activity sufficient to induce ground currents in high-latitude electrical infrastructure, and can still push auroral displays far enough equidorward that people in latitudes where auroras are not normally visible look up at their sky and do not understand what they are seeing. Meanwhile, the solar winds B's component, the component of the interplanetary magnetic field whose southward orientation is most favorable for coupling with Earth's magnetosphere and amplifying geomagnetic activity, was recorded pointing southward at the time of the most recent monitoring report. Southward B's is the orientation that opens Earth's magnetic shield. It is the condition under which the Sun's energy is most efficiently transferred into the space environment surrounding this planet. And it is pointing south this morning while 11 sunspot regions rotate in formation across the Earth-facing hemisphere. This is not a hypothesis. This is documented in the monitoring record being produced right now in real time by instruments operated by NOAA, NASA, and the European Space Agency, instruments designed specifically to detect the precursors of what could become something far more consequential than an R1 blackout over the Indian subcontinent. Think about what happened on March 13, 1989. Think carefully about the sequence, because the sequence matters. On March 10, 1989, sunspot region 5395, at that time one of the most active sunspot groups ever observed by solar astronomers, produced an X4, 5-class solar flare, X-class, not C, not MX. The most powerful category on the classification scale, that flare launched a coronal mass ejection toward Earth. 2 days later, on March 12, region 5395 fired again, an M7, 3-class flare, producing a second CME, and here is where the physics became history. The first CME, in traveling ahead of the second, had already compressed and cleared a path through the interplanetary medium. When the second CME followed, it encountered less resistance, accelerated into the cleared corridor, and struck Earth's magnetosphere with a force that the instruments of 1989 could barely contain in their measurement range. The KP index reached 9, the maximum on the geomagnetic storm scale. The DST index plummeted to -589 nanoteslas, and at 2:44 in the morning on March 13th, the electrical currents induced in the ground beneath Quebec by that storm found a single weakness in the hydro transmission system. The entire Quebec power grid lost power in less than 90 seconds. Not gradually, not regionally, the whole system, in 90 seconds. 6 million people woke to darkness in a Canadian winter, with no heat, no light, no metro, no airport, no functioning elevator in any building in Montreal. The blackout lasted 9 hours. The storm, according to Dr. David Bottler, head of the Space Weather Group at Natural Resources Canada, was the biggest geomagnetic storm of the space age. His precise description of it, the archetypal disturbance for understanding how solar activity can cause blackouts. 1 sunspot region, 2 flares, 90 seconds, 9 hours of darkness for 6 million people. The geological and astrophysical record holds one event that dwarfs even March 1989, September 1, 1859. Amateur astronomer Richard Carrington was in his observatory near Redhill, England, sketching sunspot positions, when he witnessed something no human being had ever consciously recorded, a solar flare visible to the naked eye, a blast of white light so intense it blinded him briefly through the eyepiece before he understood what he was seeing. The CME that followed that flare traveled the 150 million kilometers between the Sun and Earth in just 17.5 hours, an extraordinary speed, driven by the same mechanism that powered the 1989 event, a preceding CME clearing the corridor. The geomagnetic storm that struck Earth on September 1 and 2, 1859, produced a DST index estimated between -800 and -1,750 nanoteslas. For scale, the 1989 Quebec storm reached -589. The Carrington event was measured in some estimates at nearly 3 times that intensity. The energy released amounted to the equivalent of 10 billion atomic bombs. Telegraph operators across North America and Europe, the entire global communications infrastructure of 1859, found their systems electrified by induced ground currents. Operators who touched their equipment received electrical shocks. Some telegraph stations caught fire. The aurora borealis was visible in Cuba, in Panama, at 9 degrees north latitude. Ice core samples analyzed in subsequent decades confirmed that the Carrington event was at least twice as powerful as any other solar storm in the preceding 500 years of geomagnetic record. A 2008 report by the National Academy of Sciences estimated that a Carrington-scale event striking today's interconnected power grid and satellite infrastructure could produce economic damage ranging from $1 trillion to $2 trillion and leave parts of the United States without electricity not for 9 hours but 4 months, potentially longer than a year in the most severely affected regions due to the extraordinary difficulty of replacing large power transformers that would be destroyed by geomagnetically induced currents. The system is not hardened against what the Carrington event would do to it. The system was never designed to absorb that. This is not historical curiosity. This is the calibration frame against which today's instruments must be read, R4446, sitting in its beta-gamma configuration on the Earth-facing solar disk on May 2026 is not Sunspot 5395. It has not yet produced an X4. 5. The M1, 2 from R4455 this morning is a fraction of what the 1989 region delivered, but the Sun does not announce its intentions. It does not issue a press release before producing an X-class flare. The instruments detect what has already happened. They can assess probabilities for what comes next. They cannot guarantee the next hour. Consider the people of Mumbai. On this morning, May 30th, 2026, approximately 20 million people in the greater metropolitan area of Mumbai on the western coast of India woke up and began their day under the same sky that received the R1 radio blackout at 7:04 for UTC. The fishermen who left the harbor before dawn rely on HF radio communication for weather updates and emergency contact. The aviation operations at Chhatrapati Shivaji Maharaj International Airport, one of the busiest airports in South Asia, handling hundreds of international flights daily, depend on navigation and communication systems that operate in the frequency ranges degraded by R1 events. The millions of residents who depend on the city's electrical infrastructure, which draws on a national power grid that stretches across the subcontinent, go about their morning with no awareness that 11 active sunspot regions are rotating toward the center of the sun's Earth-facing disk, and that one of them has already demonstrated the willingness to fire. These are not abstract populations in a risk assessment. These are people who have breakfast and send their children to school and sit in traffic and go to work in hospitals and run data centers and operate water treatment plants, all of it dependent on systems that have never been required to withstand a 1989 scale event in the modern era, let alone what the instruments describe as possible at the upper end of the sun's current activity range, and Mumbai is not alone in this exposure. The question the monitoring agencies cannot yet answer, and will say so, because they choose their language carefully here, and that careful language is itself the warning, is whether the partial halo CME en route to Earth on May 31st will arrive accompanied by another ejection, or whether our 4446E's continued evolution will produce a flare in the coming days significant enough to launch a second CME that travels behind the first. The 1989 event's most destructive feature was not the size of either individual ejection. It was the preconditioning the first CME clearing the interplanetary highway so that the second could run faster and strike harder. That mechanism is not unique to 1989. It is a documented feature of how multiple sequential CMEs interact with Earth's magnetosphere, and it is a feature that becomes relevant whenever more than one Earth-facing active region is producing significant flare activity within a window of days. Right now, on this disk, there are 11 regions, one of them already fired this morning. Here is where the connected systems begin to speak. The sun's activity does not affect only radio communications and power grids. It couples with Earth's entire electromagnetic environment in ways that propagate through systems most people never associate with space weather, the ionosphere, the electrically charged upper layer of Earth's atmosphere, extending from roughly 60 kilometers to more than 1,000 kilometers altitude, is the medium through which HF radio propagates and through which GPS satellite signals pass on their way to the receivers in your pocket and in the cockpits of every commercial aircraft in flight right now. When solar X-ray radiation from a flare strikes the ionosphere, it rapidly increases the electron density of the lower layer, and that increased density absorbs radio signals rather than reflecting or transmitting them. This is the mechanism of the radio blackout confirmed this morning, but the ionospheric disturbance does not end when the flare's X-ray flux returns to background levels. The enhanced ionization persists for tens of minutes to hours, and during periods of sustained solar activity such as the period the instruments are currently monitoring, it can be refreshed and compounded by successive events. 11 active regions means 11 potential sources of ionizing radiation, rotating in a slow procession across the Earth-facing hemisphere over the coming 2 weeks, each one capable of rays striking the ionosphere before the previous disruption has fully cleared. The second connected system is the geomagnetic field itself and its coupling to the electrical infrastructure that civilization has built across the surface of this planet. Power transformers are not designed to carry direct current. The electricity that flows through transmission lines is alternating current, oscillating at 50 or 60 cycles per second depending on the country. Geomagnetically induced currents, the ground currents created when a CME's particle storm interacts with Earth's magnetic field and drives those field lines into motion, are quasi-DC currents. They do not oscillate. When they enter a transformer, they create a DC bias in the core that drives the transformer into magnetic saturation. A saturated transformer draws excessive reactive power, generates intense heat, and can fail catastrophically and permanently within minutes. A 2025 study published in peer-reviewed research examining data from the United States Department of Energy ZOE for 17 outage reports from 2006 to 2023 confirmed that years with multiple strong or severe geomagnetic storms show elevated incidences of unexplained power interruptions, outages attributed to unknown or unusual causes that standard grid analysis cannot account for. The correlation between increasingly negative DST index values, enhanced solar wind velocity, and higher numbers of unexplained outages is statistically significant. The storms do not have to be visible in the headlines for them to leave their signature in the power grid's fault record. They leave it anyway. Large high-voltage transformers are not commodity items. They are custom-engineered for specific grid configurations. They weigh between 100 and 400 metric tons. They require specialized heavy lift transportation. Manufacturing lead times in normal conditions range from 12 to 18 months. The global supply chain for high-voltage transformer manufacturing operates without a meaningful strategic reserve. If a severe geomagnetic storm were to simultaneously destroy multiple transformers across a regional grid, the timeline for restoring full electrical service would not be measured in days. It would be measured in seasons. In the interim, the cascading effects on hospitals, water treatment, food refrigeration, fuel distribution, emergency services, and communication infrastructure would compound in ways that grid operators have modeled, that government agencies have documented in classified and unclassified risk assessments, and that the public rarely hears discussed in the same sentence as a morning news report about a radio blackout over India. The KP index at the time of this report stands at 2 quiet conditions. The solar wind is at moderate speeds. The partial halo CME from May 26th has not yet arrived. The arriving blow, if it connects on May 31st, is currently projected as a glancing impact. Conditions may ramp up to active but not yet predicted to reach severe storm classification. This is not alarm. This is the current data accurately reported. But here is what the current data also shows: 11 active regions simultaneously. 1 confirmed are 1 blackout on the morning of May 30th, are 4446 with a beta-gamma magnetic configuration and an accelerating complexity trajectory, a partial halo CME in transit, solar wind B's component oriented southward at time of last reading, and a sun that is not declining from its maximum phase at the rate the original solar cycle 25 predictions anticipated. The system is not inactive, it is accumulating. Each of those data points alone is a note. Together, they form something that requires you to hold the full score in your mind and read every line at once. Think now about the second set of people who deserve to be named in this account, the engineers and grid operators in the control rooms that monitor North America's high-voltage transmission networks right now on the morning of May 30th, 2026. These are people who sit in front of monitoring dashboards that receive data from NOAA's Space Weather Prediction Center, who have procedures in place to implement protective measures reducing power flows on transmission lines, shedding load in controlled patterns, instructing operators to modify interconnector settings when a geomagnetic storm warning is issued with sufficient lead time. The keyword is sufficient. The timeline between a CME launch from the Sun's surface and its arrival at Earth is on average 1 to 4 days for typical ejection speeds. The timeline between a CME's detection by monitoring satellites such as the GOES-19 spacecraft operating the SEEK or 1 coronagraph, the first operational real-time coronagraph in history, launched specifically to provide the early warning that previous generations of engineers could not access, and the confirmation of an Earth-directed trajectory can be minutes to hours. Minutes to hours in which the grid operators must decide whether to begin protective load shedding, which means deliberately taking portions of the power supply offline to protect the infrastructure, or to wait for better data and risk being caught with the full grid exposed when the CME arrives. This is not a theoretical dilemma. It is a real operational decision made by real engineers with incomplete information in real time, and the quality of the data available to them in the next 24 to 48 hours from the 11 active regions currently facing Earth, from the CME in transit, from the B's component of the solar wind will directly determine the margin between a managed disruption and something larger. The solar maximum of solar cycle 25 produced in May 2024 what became the most intense geomagnetic storm since the Halloween storms of October and November 2003. Sunspot region R3664 generated an X87 class flare and multiple X-class events, the resulting CMEs triggering a G5 geomagnetic storm, the highest classification on NOAA's 5-level geomagnetic storm scale, with a KP index of 9 and a DST index that fell to negative 412 nanoteslas, G5. The system has already demonstrated in this solar cycle that it is capable of producing conditions at the extreme end of the monitoring scale, and that was May 2024. The sun has not quieted, we are still inside the active maximum phase, the smooth sunspot number that exceeded the original prediction by more than 20% above the upper forecast boundary is still being registered by CILSO, the International Sunspot Index and Long-Term Solar Observations Center in Brussels. The cycle is 5 years in progress. It will not reach solar minimum for several more years. Between now and then, every rotation of the sun brings the active regions on its far side, including whatever is building there, invisible to direct observation, around to the Earth-facing hemisphere again. What is currently on the far side? What the coronagraph data from GOES-19 showed on May 25th and May 26th was dramatic far-side eruptions, CMEs hurled into space from sunspot regions that have not yet rotated into Earth's line of sight. Those regions will rotate into view. The timeline is determined by the sun's 27-day synodic rotation period. What is building on the hemisphere we cannot yet see, building without observation, will present itself to Earth's facing direction in the coming weeks. The stereo spacecraft and helioseismological observations can provide partial information about far-side active regions, but far-side monitoring remains substantially less precise than Earth-facing observation. The sun keeps its next move partially obscured, and the monitoring networks watch the hemisphere they can see and prepare for the hemisphere they cannot. Here is the honest truth about prediction. NOAA's Space Weather Prediction Center, NASA's Goddard Space Weather Laboratory, and every major national space weather agency on Earth will tell you the same thing if you ask them directly. Prediction remains impossible even with the most advanced instruments currently operating. Detection is possible. Pattern recognition is possible. Probability assessment is possible. Prediction: the ability to say with certainty that a specific sunspot region will or will not produce a specific flare of a specific classification at a specific time is not achievable with any current technology. Solar physicists can examine the magnetic complexity of R4446E's beta-gamma configuration, can measure the rate at which its field is being stressed and sheared, can compare its evolution to the historical record of similar configurations that produced X-class events, and they can give you a probability, a meaningful, data-supported probability, but not a certainty. The instruments are extraordinarily capable. Prediction is still beyond them. And that gap between detection and prediction, between knowing what exists and knowing what it will do, is the territory in which every power grid operator, every aviation authority, every maritime communication network, every hospital emergency power manager, every person living inside the arc of a system that could be reached by what 11 active sunspot regions are accumulating at this moment must make their preparations. The first person to watch a solar flare with his own eyes was Richard Carrington, in a quiet observatory in Surrey, England, on September 1, 1859. He saw the flash, noted the time, and documented it in careful scientific language that he would spend years trying to explain to colleagues who found his hypothesis that a light on the surface of the sun could be connected to the disturbances their magnetometers were recording on Earth too extraordinary to accept without more evidence. The evidence arrived the next day, when telegraph lines across 2 continents went silent and then began conducting current without any battery to drive them, when the auroras appeared in the Caribbean. When the monitoring instruments spun their needles against the stops of their measurement range and could not record anything further because the disturbance exceeded what anyone had designed the instruments to measure, Carrington's hypothesis became fact. The connection between the sun and the electrical systems threading the surface of this planet was established not by theory but by the event finding those systems and showing, in the clearest language available to physics, exactly what it was capable of. Today, on May 30, 2026, the instruments are better. The monitoring is more continuous, more sensitive, and more globally distributed than anything Carrington could have imagined standing in his observatory with a notebook and a pencil. The GOES-19 coronagraph provides real-time CME observation. The Solar Dynamics Observatory captures full-disk solar imagery at multiple wavelengths, every 12 seconds. The network of ground-based magnetometers that monitors geomagnetically induced current risk and power infrastructure is more extensive than it has ever been. And yet, despite all of that, despite 167 years of advancing instrumentation since Carrington watched his white light flare and the world lit up below it, the R1 blackout this morning arrived at 7:04 UTC over India without a specific advance warning targeted to that event at that moment, because the M1.2 from R4455 was the first action that region took, and the monitoring system detected it as it happened, not before. The sun does not give us more warning than it chooses to give. This morning it chose 7:04. And R4446, with its beta-gamma architecture and its gamma component evolution and its position as the most magnetically complex structure currently facing this planet, has not yet chosen at all. 11 active regions, 1 confirmed blackout, a CME arriving tomorrow, the most energetically loaded sunspot in the Earth-facing hemisphere has not fired. Solar maximum is not ending. The far side is producing eruptions we cannot fully see. The grid remains what it has always been, an extraordinary achievement of human engineering built on the assumption of an ordinary sun, and the sun this morning on May 30, 2026 is not being ordinary. The Carrington Event reached Earth in 17.5 hours and generated a magnetic disturbance that no modern instrument was alive to measure. A 2024 reconstruction of the historical magnetogram records from Greenwich and Kew observatories found that the rate of change of Earth's magnetic field during that storm was at least 500 nanoteslas per minute. 500 nanoteslas per minute. The Quebec storm of 1989, the one that took down a national power grid in 90 seconds, produced a DST of negative 589. The Carrington Event produced estimates ranging to nearly 3 times that magnitude, and did it when the only electrical infrastructure available to be destroyed was a telegraph wire. The planet we have built since 1859, the one threaded with undersea cables and high-voltage transmission lines and satellite constellations and fiber networks and data centers running the financial systems and hospital systems and water distribution systems of 8 billion people, has never met a Carrington-scale event. Not once. And today, the same source that produced the Carrington Event, the same nuclear furnace 150 million kilometers from where you are sitting right now, is running 11 active regions on the hemisphere that faces you, at the peak of a solar maximum that exceeded every prediction made for it, on a morning when one of those regions already reached out and silenced the sky.